We talked in detail about the square previously. We talked in detail about the square law MOSFET, and we saw an equation which was generic that could be used in triode region and also in saturation region. Now we consider the velocity saturated MOSFETs. So remember that velocity saturated MOSFETs are the one in which the current does not saturate, but it has some dependence on IDS, on VDS. So when increasing VDS causes a small increase in ID. Ideally, this should not happen, but this is what happens in modern short channel transistors. So in this lecture, we are going to see a model that can describe the velocity saturated characteristic. So it's better to call this velocity saturated characteristic, and the model for this one will be called virtual source model. So we are going to study a virtual source model that applies to velocity saturated characteristic curve of transistor. So let's see. So this is the curve that we saw earlier. We have now note that in this one the ID is shown as saturated, but in the same lecture we will see that we will include the case in which it is not saturated but in fact increasing. So in a couple of slides we will come back to that. So we saw for that velocity saturated characteristic, we have these two equations in the linear region. It is this equation. Note that there is no square here. Here it is power 1. Okay, and also no square here. It is power 1. Okay, so this is the equation in saturated region, and these two equations, they happen to intersect each other at a point that is called VD saturation. And VD saturation for velocity saturated model is equal to V sat, which was the saturated velocity. We saw this earlier, that it is 10 raised to the power something centimeters per second or something. Okay, so the electrons should not move faster than this velocity. So this was the initial reason why the device were called velocity saturated, that all the electrons will be sort of saturate in the speed at this limit. But actually we will see that there are exceptions, but let's keep that to the later point. So VD sat is equal to V saturated into L by the mobility in the channel. Okay, so this is the if you have a voltage that is equal to this, you are exactly at a saturation point. Below this is the linear region, and above this is the saturated region. Now note that this was the case for square law device or square law characteristic. Okay, so What that means is that VD set in velocity saturated model is less than VGS minus VT. So the this voltage is less than that. So if you have a square law device, you will have a higher saturated voltage. So again, this is shown as another picture. So you have ID versus VDS, and the goal is that we want to connect these two regions smoothly. We want a model that can connect the linear region and the saturation region smoothly. And what that model is called virtual. So now this is the development of virtual source model. We will not exactly derive it, but we will see some of its important intermediate formulas, and then we will go to the conclusion. So we know this equation very well, that the current is equal to in the previous lecture it was written like this, that current is equal to the width times charge in the channel, okay, and times the velocity. So we have seen this formula in the square law device. The same formula is here, but the W goes on the other side in the deviation factor. So when VGS is greater than threshold voltage, then the transistor is on, and we have this equation, which was the charge at the virtual source is equal to minus Cox times VGS minus VT. Again, we have seen this equation. Second is this one. When VGS is less than VT, the transistor is off and there is no charge in the channel. Okay. Now, with respect to VDS, when the transistor is on, then we have, when the transistor is on, for this case, we may have VDS is less than VD set, which is let's say less than or equal. So we may be at the saturation point or linear region. So it is equal to this velocity is equal to mobility times VDS divided by L. Okay. So and when VDS is greater than V saturation, the velocity becomes constant. So if you are in the this is our VD set. So if you are on this side, the velocity is increasing something like this, but when you reach this point, it becomes sort of constant. So this curve is shown by this part, okay, that in this region the velocity is dependent on VDS divided by L into mobility, and beyond the VDS point it is constant at V saturation. Okay, so these are the maximum and minimum values. By maximum and minimum means saturation is the maximum value, and then in the linear region you start from the minimum and go to the saturation point. So how to smoothly connect is given by this formula. This is the main function of virtual source model. This is the main function that connects the regions smoothly. So some researchers have derived this formula, and this formula is VDS by VD set divided by 1 plus VDS by VD set raised to the power beta. So what is beta? Beta is an empirical constant that these researchers derived with a lot of experimentation, and beta ranges from 1.4 to 1.8. Okay, so there is no physical reason, but from a lot of experiments they have calculated this value for the practical transistors, and it works. So let's see how this formula can be used in different regions. So when we have VDS less than VD set, very less than VD set, this is the linear region. Okay, then in that case, the what happens is that this quantity becomes very small. When we have VDS that is very less than VD set, this quantity becomes very small. You can assume it 0. So the denominator goes away, and what remains is this one, VD set, VD by VD set. Now if we put this in here, okay, so we will get this one, which is VD set, VD by VD set into saturation velocity. And if we put the value of saturation velocity from the previous slide, okay, we will get this equation. Now this equation is exactly the equation that describes the linear region. Remember that this point was VD set, and until this point we have the mobility times VDS by L. So this whole region is described by this formula. And when we have VDS very greater than VD set, then what happens is that the denominator dominates, and you can neglect 1 in comparison to so I can write something like this. So I can write something like this, that when this is the case, what happens is that VD set by VD by VD set is very greater than 1. Okay, and in the denominator this dominates, and 1 can be neglected, and then if you do the math, you will get that VD set, if set is approaching to 1, and when if set approaches to 1, according to the first formula, this one, VDS, the velocity, which is a function of VDS, reaches the saturation point. So you see this one formula, formula number 1, explain both the linear and the saturation region. Okay, now we come to the point of finite resistance. So we saw that there is a slope here, which means that increasing VDS increases the current a little bit. Okay, so again we start with the formula for the current. This is the one that we know. We know that the charge is this one, and in order to understand where resistance comes from, we have to understand this formula. Now in this formula, the rho is basically Dibble. And what Dibble mean? Dibble means that Dibble means that an increase in VD, which is the drain voltage, okay, reduces the threshold voltage VT. So we have seen that earlier, that for example this was our conduction band and this was our energy band diagram. Now maybe let me use a different color. So maybe the original one was like this, okay, but a higher VD, okay, this is VD2, a higher VD, and this is VD1. So VD2 is greater than VD1, and it brought down the Fermi level on the drain side, and it also brought down the potential hill. So it made it easier for electron to jump from the source to the drain side. So as it has become easier for electron to jump from the source to the drain side, so the resistance has reduced. Okay, so you can understand that Dibble is a mechanism of that you can interpret as resistance. Okay, so it basically lowers the threshold voltage, and it makes the easier for electrons to flow from one side to the other side. So this is where the linearly sort of increasing curves come from. So we have accommodated this in the virtual source model. Then now we know this is the equation for the linear region, okay, and this whole thing can be considered as 1 by R. Okay, so V is equal to IR, or I is equal to V by R. So this is what is called channel length, and it is the slope of this black line. Okay, so this is called the channel length or on resistance. Now you see, whenever you use the transistor, so there are contacts, for example for VDD and for gate and for other things. So there is some resistance between the drain and the VDD, and between the source and the VS or ground. These are called parasitic resistance. So let's see that how the these parasitic parasitic resistances can be included in our model. So we have this VG prime, okay, which denote the intrinsic gate voltage. So all the primes are intrinsic gate voltages. For example, VG prime means intrinsic gate voltage, VD prime means intrinsic drain voltage, VS prime means intrinsic source voltage. So VS prime is here, is the voltage here, VD prime is the voltage here. Okay. So in case of a gate, it's simple that there is no resistance. We have seen in the previous slide that the resistance with the ground is only important in RF application, not in digital application. So that's why we have neglected that. In the case of drain, the VD prime is equal to VD minus IR drop across the RD. So ID is a function of VG prime, VS prime and VD prime into RD, and VS prime is the voltage here. So it is equal to the voltage at this point plus the drop is in this direction, so we have to add. So it is equal to VS plus ID into RS. So in this way we can accommodate the effect of these two series resistance. And if we plot it, so if the black one is the curve for intrinsic model of MOSFET, then the curve with series resistance drops in all the regions by some factor, and it is below that voltage. So we see that we can include the effect of these parasitic resistances. So this is our virtual source model. Now you see here it is written level 0. So level 0 because this is the first version of virtual source model, and there are different phenomena that occur in very latest technology transistors that may not be included in this simple model. So there are versions of this model that are more suitable for latest generation of transistors, but this is the first one which is which can describe the velocity saturated transistors in some detail. Okay, so the whole model is consisted of 5 equations. We have the equation for current, okay, we have the equation for charge, which is minus Cox times VGS prime minus VT, and when we have this equation, this is the equation from Dibble. Then we have this equation which has the saturation function, and then we have the formula for saturation function, and then we have the saturation voltage as a function of saturated velocity, channel length and mobility. So there are some these are the equations that describe the virtual source model. So but there are, as I told, there are things that cannot be described by this simple model. We will maybe we will come back to this or not. We will see how much time we have. So let me skip this one, but this is for example one exception, that the velocity saturated model assumes that the velocity should be maximum this one, okay, but in reality the velocity is something like this in modern transistors. Okay, in modern transistor it is something like this. So you see the velocity goes way up above 10 raised to the power 7 centimeter per second. And why is that? The reason is that the scattering, So scattering is a phenomena in which the electrons collide with the surface of oxide and with the atoms, and it moves. Sometimes it is reflected, sometimes it is deflected. Okay, so that scattering does not happen. Okay, ideally it should happen, and this is that this it is the scattering that saturates. So the reason for velocity saturation is scattering, but in very latest transistors, the velocity does not saturate, but it overshoots. Okay, so this is something that the virtual source model cannot accommodate. This is one exception that is not explained by the velocity saturated model. So as we know that transistors are getting smaller and smaller, there are weird kind of phenomena and weird kind of physics that is coming into play. Okay, so this is one of them. And what has happened, in order to explain that problem in this previous slide, there are two kinds of transports in the modern transistors. So this we call transport. One is diffusio transport, and the other is ballistic transport. Diffusio transport is the normal one. For example, you have this electron, it goes, and then there is some hindrance, and maybe it comes back. So this is scattering, reflection or something. But the ballistic one is something like this, that the electron just shoots across the channel from source to destination. The electron sees this whole region as vacuum. So that's why it's called ballistic transport. There is no resistance to flow of electron. Okay, so in the ballistic transport, there is no resistance to the flow of electron, and that's why it's called ballistic transport. Okay, so let's stop our discussion here, and this is to summarize. This was the lecture about the virtual source model, which explains the velocity saturated IV characteristics, and we have seen how we can smoothly connect the linear and saturated region. We have also seen how the resistance in the saturated region can be included through Dibble effect. We have seen how parasitic resistances can be included. We have seen the problem of velocity overshoot and the concept, let's say very initial intro of the concept of ballistic transport. Okay, so ballistic transport is a wide topic, but we are just naming and sort of giving you an initial definition. So let's stop here.